All right, so welcome back to your 9.2 video notes. So in 9.1, we looked at the beginning of just hypothesis testing and significance test, introduced some things. Some of the things that we are doing in this lesson is going to require you to have watched 9.1, specifically looking at interpreting a p-value, your decision slash conclusion. So, with that said, what we saw in 9.1 is that Mr. Gomez may not have been the 80% free throw shooter he claimed. And in fact, we saw that we rejected our null hypothesis and we had convincing evidence that Mr. Gomez is a less than 80% shooter. So, what that looked like here, what we just said is we were testing this claim that our null hypothesis is that Mr. Gomez is an 80% free throw shooter versus that alternative hypothesis being that he's not and he's a less than 80% shooter. One thing that's important here, you always want to define your parameter. This parameter P is the true proportion of free throw makes by Mr. Gomez. And another thing that's important here, when we go through and do this stuff, the math requires us to assume that our null hypothesis is true. Now, when we get to our conclusion, that doesn't mean, hey, is the null true? We don't have that. We can't say that. But when we do the math, our math requires us to have a p for the true proportion, and that is where our null hypothesis, we just assume it's true so we can do the math. What you're going to notice now, do we have a random sample? So when Mr. Gomez shot his 50 free throws, the question you want to ask yourself, were all of those shots random? And they'd have to be. It's not like he could pick out 50 makes. He actually had to do them. They're random. So yes, we do have a random sample. Why is that important? So we can generalize to the population. We're always wanting to generalize to our population. Is the 10% condition satisfied? So here, remember the 10%, if you need this, is that your sample size is less than or equal to 10% of the population. Here, our sample size is 50, and that is less than 10% of all free throws that Gomez could attempt. He could keep going forever with these. So, all free throws, yes. Why do we care? Now, some people talk about independence and whatnot. I just think the easiest way to say this is so sampling without replacement is okay. Easiest way I found to say that. Next thing we'd want to do, we do want to check our large counts condition. We're going to talk about why, but when we check this large counts condition, it's really important to note you have a couple things here. You have a p of 0.8. That is your null hypothesis. You also have a p hat that states 32 out of 50, which is 0.64. Which one do you use? We're going to be using our p. That's why I said up there you assume the null hypothesis is true. We're going to be using p. So n times p and n times 1 minus p, these both have to be greater than 10. So let's check. 50 times 0.8, which is 40. Yep, greater than 10. Okay, 50 times 1 minus 0.8. This ends up being 10. And while it's not greater than 10, it is equal to 10. So these check out. Why do we care? So the sampling distribution of p hat is approximately normal. Again, that's really important here. It's so that we can now use a normal distribution to do things that we need to. Now, find the mean and standard deviation. As a reminder, for a one sample proportion, the mean of p hat is just p. Here it's just 0.8. The standard deviation of a one sample proportion is the square root of p times 1 minus p over n. Notice we're not using p hat, we're just using p. So here, square root of 0.8 times 0.2 over 50. This is going to give us 0.057. Okay, your note here on 4 and 5, use p, not p hat. Again, that's because we're just assuming our null is true. We want to do all this math for 0.8. All right, so now this kind of gets a little weird. We're going to use this for number 6. It says label this. So we have here our normal distribution with a mean of 0.8 and a standard deviation of 0.7. Now, one thing we don't do a lot of is because we have Desmos, and I will show you Desmos. But just as a reminder, you know what one standard deviation or two standard deviations or three standard deviations away is. If we take 0.8 and we want to know what's one standard deviation below it, what's that value? We would do 8 minus our standard deviation. That's going to give us one standard deviation. We can do it again for two standard deviations, and we can do it again for three standard deviations. And we could also do it up here as well. Now, is this a requirement? By no means is this a requirement that you have to do this. I'm just reminding you, you do have that ability. What we care about specifically, though, is that somewhere in here is our p hat of 0.64. We're trying to figure out what's the probability that that happens purely by chance, because that helps us determine what we have to make a conclusion on for our hypotheses. Now, just as a reminder too, this here is your sampling distribution of p hat. It's normal because of large counts, so we can use it. So we're trying to find that. Again, we're going to talk more. If you use Desmos like we're about to, we would want to draw. You don't have to draw your 1, 2, and 3 standard deviations away. You do want to draw that middle and the bound. Okay, so now let's talk how many standard deviations below the mean is 0.64. And we talked about it's a z-score. You see that here. What we're trying to do is we're beginning to build these z-test statistics. Now we've been doing the z one for a while, so this is going to feel pretty okay. What we're used to is that our z-score is x times the mean divided by standard deviation. X being the value we're given, and then mean standard deviation. We already know those. For us, plugging in these numbers would give us a z-score of negative 2.81. So we're above, we're between 2 and 3 standard deviations below the mean. And specifically, it's 2.81 standard deviations. Now, not to scare you, but we wouldn't actually use this formula. The formula we would use is p hat minus p divided by square root of 1 minus p, or sorry, p times 1 minus p over n. And look, these things all relate, right? I mean, you have here 0.64. That's your p. 0.8, p hat and p. And then you have the 0.057. That's just the square root in the denominator. So don't let those scare you. This is the math you're doing when you plug in these values. Okay, so now let's do some of the scary stuff. Find the probability of an 80% free throw shooter making 32 out of 50, which is our p hat of 0.64 or less. We've already drawn that. Now we just got to use Desmos. In fact, we could also just use table A and it could help us get there. But let's go have some fun and use Desmos. Okay? So inference, probability distribution, normal with our mean is 0.8 and our standard deviation is 0.057. Okay. Cumulative probability, and we want to be to the left of 0.64. What you'll see, really small probability down here. And our probability 0.0025, we can round to 0.003. What I want to note though, this is just a conditional probability of p hat equaling 0.64, given that they're an 80% free throw shooter. So conditional probability way back in unit 5 in December. So hey, the maths, and it all relates to each other. Now, what conclusion can we make from this? This is where you have to reject or fail to reject your null and state if you do or do not have convincing evidence. For today's lesson, we're going to use our alpha value to be 0.05. So if our alpha value is 0.05, because our value of 0.003 is less than 0.05, we will reject our null hypothesis. And we do have convincing evidence that Mr. Gomez is a less than 80% free throw shooter. Because again, this alpha value of 0.05, our probability, our p value is less than 0.00 or 0.003, less than 0.05. Okay, so now we're going to change it up. I highly suggest if you're watching this, like do it on your own and then come back. So pause the video, do 10, come back. And now that you're hopefully paused it, but you probably didn't, we're going to suppose that Mr. Gomez made 36 out of 50 or 72% of his free throws. So we're going to calculate and interpret a p-value and make a conclusion. What I want to point out here, you can do a z-score. We're using the same mean and standard deviation. You would get that this is 1.4 standard deviations below the mean. You could easily use table A here because you don't have to draw a distribution here. You can use table A. You can also go here and look at now being 0.72 and get our p-value of 0.08. However you want to do it, our p-value equals 0.08. Now, again, what we're going to do first, we're going to interpret the p-value. So, assuming the null hypothesis is true, which is that our true proportion is 0.80, there is a 0.08 probability of getting a p hat of 0.72 or less purely by chance. Little bit larger than our 0.003. What we're going to do next is we're going to make a decision and a conclusion with context. So this is where we do the because our p-value is less than or greater than alpha, we reject or fail to reject the null, and we do or do not have convincing evidence of the alternative. So here, because our p-value is greater than 0.05, we this time fail to reject our null hypothesis, and we do not have convincing evidence that Mr. Gomez is a less than 80% free throw shooter. Ooh, lots of writing. So, because our p-value is larger than our alpha value, we would fail to reject our null hypothesis. And we do not have convincing evidence that Mr. Gomez is less than 80% shooter. So, that what we did at the end is really coming from 9.1. So what do we do in 9.2? There's two things. And again, this is not one of these lessons that is eye-opening because we're still in the world of proportions. We still have three checks we have to do. We have to check if this is a random sample so we can generalize to the population. We still have to check if our sample size is less than 10% of the population. That way we can sample without replacement. And we still have to check the large counts condition so that we can use an approximately normal distribution for our sampling distribution. The large counts we really care about because if we can't use an approximately normal distribution, it's going to be harder for us to calculate our p-value because we require our test statistic with a z-test statistic. The second part here, this calculate test statistic, is your statistic minus parameter divided by standard deviation. We've been doing that for a while now. It just looks funky because I can make it be p hat minus p over the square root of p times 1 minus p over n. Don't let that scare you. Just know that's how we find it for a one sample proportion we're dealing with right now. Finally, and this is kind of a key idea here, when we talk about that p-value, it's just the area, right? It's similar to what we've been doing forever. This one here would be p greater than whatever this is, because it's over here. If it were somewhere over here, we'd be looking at p less than. So just as an example here. All right, guys, that's it for your 9.2 lesson. Hopefully y'all have a great day. Make sure you do this check your understanding. It's going to walk you through everything you have to do. Peace.